That was the song of the summer, Call Me Maybe by Carly Rae Jepsen. I don't know about you, Lucas, but I don't think I'll ever get sick of that song.
No way, I could see myself listening to this in 7 years. But I don't know if this song of the summer. Have you heard of the new track from Wasabi and Master E, Love Physics? It's straight fire.
Okay, before we get back to the hits that you want to hear, we have something everyone needs to hear about.
Definitely. Now, I'm no scientist, but I hear there is stories that are making headlines. The Higgs boson, an elementary particle of the atom, has been discovered by researchers at CERN, the European Organization for Nuclear Research. Apparently, the particle's discovery was groundbreaking in the physics community, and we have brought in two scientists from CERN to give you, the listeners, some information on the matter.
Introducing Dr. Crabtree and Dr. Chua. Thank you guys so much for coming in to FM Swerve 96.9. It's a
It's a
pleasure.
pleasure. Now, I remember learning about Bohr-Rutherford diagrams back at school.
Does the Higgs boson fit into this theory?
The Higgs boson unfortunately does not fit into this theory, but on the topic of Bohr-Rutherford diagrams, we'll delve into the origin of Niels Bohr's atomic theory.
The origin of the Bohr model, commonly known as the Bohr-Rutherford model, was first proposed by Niels Bohr in 1913. It was heavily influenced by the works of Ernest Rutherford and considered an extension of the Rutherford model.
You mentioned that the Bohr model was influenced by the model created by Ernest Rutherford. Can you elaborate on why it is an extension of this model?
The Rutherford model was proposed in 1911 by Ernest Rutherford in his gold foil experiment. He determined through this experiment that atoms had a tiny and heavily positively charged nucleus, surrounded by a cloud of negatively charged electrons that circle around the atomic nuclei at a great distance. With this information, he created the planetary model. The big flaw with this model is that it defies the laws of classical mechanics. Since the electrons are constantly changing direction and accelerating, it would emit electromagnetic radiation, thus causing it to lose energy and collapse in towards the nucleus of the atom, signifying matter is unstable.
However, it is known that matter is stable and thus disapproves Rutherford's model. Knowing this, Bohr ultimately explained and solved the flaws that came from this model. Bohr focused his studies in the area of spectroscopy, and using a spectroscope, he studied and analyzed light emitted by elements. Bohr had two main postulates. The first postulate is that atoms have specific fixed energy levels, in which electrons are found. In these constant energy states, electrons revolve around the nucleus without radiating energy. This is the ground state. On top of this, electrons cannot be found between energy levels. The second postulate states that electrons can jump to higher energy levels by absorbing specific amounts of energy or quanta, and are considered to be in an excited state in this case. The reverse is also true in that electrons release specific amounts of energy as electromagnetic radiation when excited electrons return to lower energy levels. He then applied the quantum theory of light proposed by Planck and Einstein to explain his experimental findings. This allowed him to calculate various properties of the atom, such as the orbital radius or the energy and frequency of light emitted or absorbed.
The Rutherford model has several flaws addressed and solved by Bohr's model. Does Bohr's atomic theory have any notable flaws?
There are several limitations to the Bohr model. It is limited in terms of size and overall does not function well for multi-electron atoms, meaning when larger atoms are in question, poor spectral predictions are obtained. Another huge shortcoming of this model is that it violates the Heisenberg uncertainty principle. It states that it is impossible to know the absolute certainty of both the position and momentum of an object beyond a certain measure of precision. Now that we understand the Bohr model, a relatively simple model of the atom, do you think you could explain where the Higgs boson fits in the field of particle physics?
Well, the Higgs boson is a part of a wholly different theory of the atom. It is part of the Standard Model. Once we explain this, you can begin to understand how the Higgs boson fits in. The first thing to understand is that the Standard Model stems in many ways from the Bohr model. For a brief period in time, it was generally thought in the scientific community that the Bohr model was correct, and that the only subatomic particles that existed were protons, electrons, and neutrons. One of the first developments that disproved the Bohr model came in the 1930s, when P.A.M. Dirac
Predicted the existence of the positron, essentially an anti-electron. This particle has the same properties and characteristics as an electron, but has the opposite charge. Positrons are an example of antimatter, which exist for other particles such as neutrons, which have antineutrons, and protons, which have antiprotons. We'll come back to antimatter later on.
The idea of only 3 subatomic particles did not last long, though, and very quickly other subatomic particles were discovered. One of the first revelations was that protons and neutrons are composed of quarks and antiquarks. Quarks are fundamental particles with charges of 2/3 elementary charge or -1/3 elementary charge. Protons, neutrons, and their antiparticles are part of a family called hadrons, defined by the fact that they are composed of quarks.
Leptons is the other family of elementary particles. It includes electrons, muons, tauons, and their neutrinos. A lepton is currently understood to be indivisible.
Yes, but before we get into that, I need to explain a bit more about quarks. There are 6 flavors of quarks: up, down, charm, strange, top, and bottom, all with different masses. Hadrons are composed of a combination of these quarks or their antiquarks. A proton, which is a baryon, meaning a hadron of 3 quarks, has 2 up quarks and a down quark. This can be noted as UUD. Neutrons are also baryons. Mesons are hadrons composed of 2 quarks. Pion, or pi plus, is a meson of an up and an anti-down quark.
Now moving on to leptons. Each lepton has a corresponding neutrino with charge 0 and a very minuscule mass. The electron neutrino has a mass of less than 100,000 times the mass of an electron. Okay, so now there is a bunch of tiny particles out there. But what is the purpose of them? And is the Higgs boson a quark or a lepton?
Well, quarks and leptons, the particles we just explained, only really tell half the story of the Standard Model. Quarks and leptons are the basic building blocks of matter, but do not form the Higgs boson.
Have you heard of the 4 fundamental forces?
There is another type of particle that is responsible for the fundamental forces of matter, the boson.
The Higgs boson?
No, we're getting to that.
The Standard Model accounts for 3 of these 4 forces.
The strong nuclear force, the weak nuclear force, and electromagnetism. The strong nuclear force holds nucleons together. The weak force causes radioactive decay in atoms, and electromagnetism causes attraction and repulsion between electric charges. Bosons are the subatomic particles that transmit these forces through quarks and leptons, which are classified into a group called fermions. The first type of boson worth knowing is the photon. The photon transmits electromagnetic force between charged particles. The strong nuclear force is transmitted by gluons, of which there are 8 different types. Finally, the weak nuclear force is mediated by the W+, W-, and the Z bosons. You can essentially think of bosons as carriers of force. Okay, but can we hear about the Higgs boson already?
Yes, as you've heard, the Higgs boson was discovered today. Although the details about this particle are still largely unknown, the Higgs boson is a particle instrumental in giving other fundamental particles their mass.
Wow. So, now that they've found the Higgs boson, is there anything left to discover for future scientists?
Well, as some of you may have noticed, when we mentioned the 3 fundamental forces, we left one out: gravity. The Standard Model does not account for this force, and it is hypothesized that to get a better grasp on how our world works, we must combine the Standard Model with the modern theory of gravity and relativity theories into one theory of everything.
Wow, that's so cool. But earlier you mentioned something about antimatter. Can you expand on that and talk about matter and antimatter?
Well, antimatter is very mysterious and interesting. It is said that when the Big Bang occurred, matter and antimatter should have been formed in equal amounts. When they meet, they annihilate each other, producing energy. Thus, in theory, the world and all of us should not exist. It is also assumed that there is 1 extra matter for every billion matter-antimatter pairs. What caused this asymmetry is still unknown to scientists at CERN and all around the world.
Interestingly, antimatter is extremely rare. In fact, the CERN Particle Accelerator has created a grand total of 2 nanograms of antimatter. If all the antimatter ever created by humans was annihilated at once, it would not even produce enough energy to boil a cup of water. The main problem with antimatter is that it is the costliest material to make. 1 gram of positrons would cost 25 billion, while a gram of antihydrogen would cost 62.5 trillion, according to NASA.
Can you guys give us any information on what CERN is currently working on?
CERN has only produced 2 nanograms of antimatter, but we still have an antiproton deaccelerator that is used to capture and slow antiprotons in order to study their properties and behavior. Furthermore, antimatter is slowly being incorporated into the medical world. Most recently is the PET, positron emission tomography, which uses positrons to produce high-resolution images of the body. Here at CERN, we're exploring our options, and at the moment we're currently researching the possibility of using antimatter in cancer therapy.
Yes, and although we believe we have a decent grasp on antimatter in the atom, discovering more on this subject is also believed to be a key part in developing the theory of everything.